been very difficult to design our test vehicle to take that, and it will give us critical data to design the production vehicle, so we know that our components will survive there.
And you mentioned that we want to learn about these motors. We do that individually through ground tests. We've done that with each of the 3 motors, done even more than one test for some of them, to lead up to this fully integrated test. This is the first time these motors have all been connected and are being put through this very dynamic flight operation. What do we expect to learn from this test specifically? What are our objectives from this flight test?
Our primary objectives really are to learn mostly about this Abort motor, how much noise it produces and how well it performs, and that attitude control motor. The attitude control motor is really a key component. So our primary objectives are all about getting acoustics, thermal data, performance data on those motors. And the ability of the attitude control motor to maintain control, because we don't have ballast, so we're statically unstable. It's got to maintain control and reorient the capsule. So that's probably the most difficult task for us, and it's where the highest risk is that the ACM actually reorients the capsule properly and puts it in a position where we can jettison the LAS and get the chutes out. And on a pad abort, one of the critical things about a pad abort is you have almost no altitude to get your chutes out. So it's one of the design cases for a motor like this. The chutes in this test are not production-like. They're flight test-specific chutes. So we do want those chutes to come out, and but the thing we need to keep in mind is the chutes are a secondary objective of this test, and if they don't work, it's really not going to be a critical failure for this test. So we would have the vehicle crash probably on the ground if the chutes don't work, but loss of the vehicle isn't going to hurt anybody, and because there's no planned use of it. The other thing that we want to know is that 100% of the data is being telemetered to the ground. And then it's being recorded in 2 solid-state recorders on board. So even in the event of a crash, we have high probability of getting all the data back.
Okay, and you mentioned that the chutes are a secondary objective. There's a whole other team that is designing those and testing them at another Army facility. So those tests are separate. We're testing the launch abort system in this test today.
That's right. The launch abort system is the article under test, and the chutes are just hopefully there to save our test article.
We do have another video that I wanted to show here that shows how we've come together across the country. Some of these motors, one was built on the East Coast, one on the West Coast, one in the middle in Utah, and the crew module was built on the East Coast, integrated on the West Coast. So we wanted to talk about the road to get into this test that we can show that video here now.
And step 109 is complete. The ignition firing line control is enabled. Full fire.
The White Sands Missile Range in Las Cruces, New Mexico. Engineers and technicians are preparing for a very special test. The Launch Abort system is a sophisticated new rocket tower designed to pull a spacecraft away from danger on the pad and during initial ascent. For the first time, all the components of the system will work together. The test not only develops core technology needed for future spacecraft, but also directly improves the chances of crew survival in an emergency. The name of the test is Pad Abort 1. It's the mid-1960s, and the Apollo program is testing its launch escape system. At the White Sands Missile Range, a squatty rocket